Hi Year 12s, this is Mr. Lim again, and this is another video on volumetric analysis, this time systematic random error in volumetric analysis. Okay, so titrations try and determine the concentration of solutions to a very high degree of precision and accuracy. As such, we try to minimize all errors, both systematic and random. We also need to keep reliability and validity high. So we're going to talk about all four of these ideas: systematic error and random error, reliability and validity. Now, some of them are linked, but we have to kind of understand them fully to be able to answer exam questions. So, random error. It is the uncontrolled effects of measurement, equipment, procedure, and environment on a measurement result. So straight from SCARSA. Things such as variations in temperature during the experiment. That's going to be an issue. Uncontrollable effects like the increments of measuring equipment. Okay, what do we mean by the increments of measuring equipment? Let's have a look. Okay, that's also related to the magnitude of random error for a measurement result can be estimated by finding the spread of values around the average of independent repeated measurements of the quantity. So, the magnitude, the amount of random error for a measurement result can be estimated by finding the spread of values around an average of independent repeated measurements. Okay, so it's just about the repeated measurements, so trials. The spread of those values that you measure for those trials gives you an idea of how much random error you have. Okay, so the spread of values will be based on your precision of your instruments. When measuring a value, you need to see which increment it is closest to. We only have confidence in the measurements from halfway between each increment. Or in other words, we are uncertain whether the value is above or below half of the value of the increment. That is its uncertainty. Okay, so for example, if I have three values here, 0, 1, and 2, and my meniscus is sitting somewhere here. Okay, so we know that it's closest to 1. However, if we said it was 1, any value that was 1 would fall within that range. Okay, halfway between 0 and 1, and halfway between 1 and 2. Any values in that area would be counted as 1. So this we would call 1 plus or minus 0.5. Okay, that's how we would measure it. And now I know that we've been talking about measuring burettes to 2 decimal places, but this is the concept of uncertainty rather than being able to read something that accurately, which I expect you all should be able to do. All right, so if the burette has increments of 0.1, then we have confidence of half of each of those increments, which is 0.05. And if a measuring cylinder, which is increments of 0.2, we can only say that it is confidence in those values between plus or minus 0.1 of a mil. Right? What you'll notice is that as you increase those increments, your uncertainty increases, which means that you will the bigger the increments, the less certain you are of it, which means the larger the random error. Okay, so during titrations, you read the burette twice to get the volume of the titer, which doubles the uncertainty because you have to take into account the first uncertainty and the second uncertainty. In calculations, if you are multiplying two values with uncertainty, you multiply them together. So calculations, you multiply uncertainties. When you're reading something, you double it, which is the sum effectively. All right, so this is a question from 2 years ago, the 2018 WACE exam. This was asking you. You've got a before and you've got an after. Okay, so let's read these two burettes. That is, this one is 4.9 or so. This one is 30.3. Okay, the difference between those is about 25.4. Okay, now each of those is a plus or minus 0.05. That means that when you have total, you've got plus or minus 0.1. So looking at the possible answers, this one actually is the only one that is A, close to the value, and B, has the right plus or minus uncertainty. Okay, so that's just an example of a question. You can minimize random error, but you can never completely remove it. Okay, so if you choose more precise equipment, so scales with greater number of decimal places, so you might have one scale that can read to 2 decimal places, or you can choose one that reads to 3 decimal places. That means that the increments are smaller in this one, which means that you have more certainty or less uncertainty or less random error. Okay, random error is always random. Okay, so sometimes you'll get asked to define random error. What you would define is that you can talk about those the uncontrollable effects of various stuff, but you can also talk about that the value that you measure will sometimes be higher and sometimes be lower, right? But never skewed in one direction. Okay, so it'll be skewed in both directions, or it's called non-directional. Okay, so skewed in both directions, high and low, or non-directional. Okay, so those are your two things that you might say when you're talking about random error. If you repeat measurements, the average of your results, your random error will decrease. Okay, so the more measurements that you take, the lower your random error gets, because ideally, if you're doing everything in the right process, your measurements get closer to the true value. Okay, so let's have a look. Next is systematic error, the contribution to the uncertainty in a measurement result that is identifiable and quantifiable, i.e. the imperfect calibration of measurement instruments. So that means that this error is one that skews the results in one particular direction, which means that the results are always going to be above or below, or always below. Okay, the true value. Things that can cause systematic error: not measuring the volume and the meniscus properly in the pipette. Okay, so say that your pipette, here is the line, and then you always get the meniscus there. You're always going to have a systematic error there because you're always going to be delivering slightly less than what it's supposed to be. If you accidentally dilute one of the standards, okay, that means that's going to always have a lower concentration, which means there's going to be problems. Or if you misread the scale when preparing the primary standard, then that's going to carry on through your entire titration. So this is an example of a question from an exam, WACE exam, can't remember what year. Scientists were given the task of investigating the concentration of dissolved heavy metals in an abandoned open-cut mine that had been filled with water to create small freshwater dams. Using a map, scientists identified 180 locations containing abandoned open-cut mine become freshwater dams. Scientists decided to randomly select locations to take water samples. The procedure of water sampling was taken below as follows, blah, 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 blah. Outline the difference between random and systematic errors, so that's just defining them. Give an example of each that might be encountered in this investigation. Okay, so let's have a think. The difference between them, so you define them, and give an example of that might be encountered in this investigation. So you got to look for things that can either A, be random error, something that would be measured above and below, and then something that would screw it up only in one direction. Okay, so you're looking at this one, you might be saying, okay, for water depth of 0.5 meters, that might be random. Okay, because what might happen is that if this is 0.5, the researcher might collect from here, and some researchers might collect from here. You're taking from 180 locations, so you're not always going to get it exactly on 0.5 meters. Okay. Systematic error, accidentally putting in a different acid, like, or even a base in there, which would precipitate all the heavy metals, which would be very bad. Okay, so adding a base instead of an acid, which would be a systematic error, right? If you didn't wait 8 hours, if you always waited slightly less, or if you pressed 8 minutes instead of 8 hours, because that's totally something that would happen, then that would make a significant systematic error. Okay, so let's have a look at what the marking key says. Okay, so marking key says, here is your definition of systematic and random errors. Okay, some examples: concentration of heavy metals vary at depth. So about depth, okay, so what this one is saying is that the heavy metals might be more concentrated deeper or less concentrated deeper, something like that. So you never know. So just collecting at one was not going to help. All right. Different collectors at different sizes are always going to collect randomly spread data. Okay. when the results are always skewed in one direction, things like faulty timers, the concentration of nitric acid is not always the same, or that you've accidentally added a base, totally screws it up. Okay, so this is what the markers had to say about this particular question. In part A, many candidates knew the definitions of random and systematic error, so that's fine. That's that part and that part. That's this part and this part. But gave examples that were ambiguous. What does ambiguous mean? Is you need more detail. Might have said depth of water, right? If you just say depth of water measured incorrectly, right, it could be random or it could be systematic, right? So if it's random because you're saying, okay, the scientists aren't going to collect it exactly the same way every single time, then that's random. But if it's systematic because your tape measure is broken and so you're measuring it at 40 centimeters instead of 50 centimeters, that's always going to be a systematic error. So you need to be specific with your answers. That's exactly what they say there. Okay, so try and be as detailed as you can. I know it's only worth 1 mark, but make sure that you're clear about, okay, this is what screwed it up. Okay, other important concepts are reliability and validity. So reliability, the degree to which an assessment or instrument or protocol consistently and repeatedly measures an attribute achieving similar results from the same population. Okay, if the data you produce the same results every time you test it, it's said to be reliable. That's why we look for concordant results, because it says that we have low random error. If you're unable to consistently produce the same result, it may be things like, whatever's increasing your random error. Not getting the meniscus on the line every time, but sometimes you get it above, sometimes you get it below, because you just don't know how to do it. Not being able to add single drops to burette, because then you sometimes get it right, sometimes you don't get it right. Okay, and if you only do one trial, you're going to have no idea if your process is reliable or not. Then it's validity, the extent to which tests measure what it was intended to, the extent to which data, inferences, actions produced, tests, and other processes are accurate, will give the right result. Okay, so does it measure what was intended? Okay, so if you use the wrong primary standard, you're going to get something that's way off and it's not going to be valid, because you're going to be kind of testing something wrong. Or if you use the wrong equations, you're just not going to get what you intended to try and get. Here's an example of something about validity and reliability. Okay, so a group of Year 12 students wanted to know whether increasing ocean acidity increases the rate at which seashells dissolve. They went to the beach, got some seawater and some seashells, crushed the seashells, put them in some beakers and they weighed them. Then they split the seawater into 5 portions and bubbled carbon dioxide into 4 of the portions, different amounts of time. Gave students natural seawater plus 4 seawaters with different pHs. Okay, so you just added some gas, make it more acidic. The various seawaters are then added to the beakers, and then the weight of each beaker was recorded at timed intervals. Which of the following pairs of statements on validity and reliability of this investigation is correct? Okay, so validity, is it measuring what you expect it to measure, and is it going to give you accurate results? So, a couple of things about multiple choice. Always look for patterns. Okay, so what I will immediately notice is that A and D and B and C are linked because they actually give the exact same thing each time. So if I know that one of these 2 is right, so therefore I can eliminate the other 2 immediately. So let's have a read. Okay, it is valid because the investigation allows them to determine if seawater pH affects the rate of seashell dissolution. Okay, it is not valid because the investigation was not simulated in a lab and not performed in the real ocean. So let's have a think. If you are going to perform something in the real ocean every time you want to do an ocean study, that's going to be very difficult, and that's going to be unreliable because, well, I mean, that's just going to be terrible because imagine having to change the pH of the entire ocean just to do a test. Okay, so we're really going to eliminate these 2 possibilities immediately because that's not the meaning of validity. Okay, let's have a look. It is valid because the investigation allows them to determine if seawater pH affects the rate of seashell dissolution. Is that what they wanted to find out? Yes, it is. From up here, ocean acidity increases the rate at which seashells dissolve. They got 5 solutions with different pHs, dump some seashells in there. That's what they're trying to do. So now we only have to look at these 2. It is reliable because the trials were performed in a laboratory. Okay, and is reliable. Of a reliability could be improved by conducting multiple trials at each different pH level, because they only did it at 1 pH level each. That's not very reliable. So this is much more accurate, and this is probably not very accurate because just because you're in a lab doesn't actually mean that you're going to do anything right. Okay, so the answer was D. Okay, so this diagram gives you a bit of an example of when you're trying to hit something, do you have high random error or low random error or high systematic error or low systematic error? So ideally we want low error in each. So this is the one with low systematic and low random error. Okay, let's have a look at this one here. We can see that all of the shots have been skewed to one side, right? And they're not even clustered very closely together. So this has a low systematic, high systematic error, high systematic error, which is what we don't want. That's why they're all skewed to one side. And it also has high random error. Okay, high random error. So it's all skewed to one side. That gives it systematic error. The high random error is the fact that it's taking up so much area and they can't ever get it to give the same result twice. Okay, here where they're all clustered together, but you notice that they're away from where they're supposed to be. So this has a high systematic error, but low random error, which means that they're going to get everything close together because their magnitude of random error is low, but you've got something wrong with your process that is always skewing your results to one side. Always skewing your results to one side, even though all your results are clustered together well. So it's like getting concordant results, but you've done something wrong in the process and they're always too high. Then finally, we've got this one here. Notice how they're all spread out, but they're all spread out around the center, which means that your process is probably doing well. Okay, your process is doing well. So you have low systematic error, but you're going to have high random error because you can't get all of your results to repeat consistently. Okay, so this diagram shows the idea that you can have systematic and random error in varying amounts, right? Ideally, we want low systematic and low random error. Okay. Now, you should be able to identify the effect of a systematic error has on a final value of a titration. It will either increase or decrease the calculated concentration. You have to work out the initial change, then all the subsequent changes to concentrations of things. If it is a systematic error, it'll increase or decrease the value. If it's a random error, it'll be more widely skewed. We're not going to have to be able to identify. We're going to have to suggest possible sources of random error, but not identify whether it will increase or decrease the value, because that's not how random error works. Okay, so here's an example. In a titration of a standard base against an unknown acid, standard means that it's your known, where the base is in the conical flask and the acid is in the burette, it's super important to know where stuff is. Okay, what would be the effect of the incorrectly measuring using the pipette by measuring the volume of the base using the top of the meniscus on the mark? Okay, so here's your pipette. Okay, here's your mark. If you're always using the top of the meniscus on the mark, that means that that volume is a low volume or a lower than what you wanted volume. Okay, so not enough base is added to the conical flask. That's important, right? If there's not enough base in the conical flask, there's too few moles of base in the conical flask. Too few moles of in the conical flask, and remember the conical flask is our known, the base, then the titer volume will be too small. The titer volume will be too small. Okay, so there's not enough moles of base in the conical flask, or less than what you wanted. that means the tighter concentration, the tighter volume will be too small. And then the too small titer means that the concentration of the acid would be calculated as too high. So what you've said, okay, if I said, I've got 20 mils of 0.1, right? That's what I should have. But in reality, I have 19 mils of 0.1 mole per liter base. Okay, that means I'm going to need 19 mils of 0.1 molar acid. And so if I had it this way, I would know, okay, then they're equal concentrations. But if I'm comparing this to this, I would say, okay, well, this one needed 20 mils, and this one only needed 19 mils. So I actually don't know what this is my unknown, right? So I don't actually know what this concentration is. Okay, so if it's equal, then I say, okay, well then the concentrations must be equal, right? But since this one here, you need less acid, that means that it's going to be more concentrated than the base. Okay, so if the volumes were equal, then you'd say the concentration was equal, right? If this one is lower, then you'd need less acid, therefore the base, it is more concentrated than the base, right? And therefore your calculated concentration would be too high. Okay, it's a bit complicated. You need to just follow it along as best as you can. Another one, the titration was performed of a solution of hydrochloric acid with an unknown concentration against a primary standard of sodium carbonate. Aliquots of the primary standard were used to standardize the hydrochloric acid in the burette. The primary standard was created using sodium carbonate decahydrate, but the experimenter thought it was anhydrous sodium carbonate. Will he calculate a too high or too low concentration of hydrochloric acid? So we know that it is actually the Na2CO3.10H2O. That's what we know that it is. However, the experimenter thinks that it's only Na2CO3. So if I have 5 grams of this and 5 grams of that, this one here is going to have less moles of Na2CO3 compared to that. Okay, so he used sodium decahydrate, but he thought it was anhydrous sodium carbonate. So when he calculates it, he says, okay, I need 5 grams of it. He measured out so he needs 5 grams. He thinks, okay, I need 5 grams of sodium carbonate. When he measures out 5 grams, that's fine. However, it's going to have less moles of sodium carbonate within that because he's actually used sodium carbonate 10 decahydrate or decahydrate. So the mass of sodium carbonate decahydrate will contain less sodium carbonate than expected. So the concentration of the primary standard will be too low. Now the primary standard gets put into aliquots, right? So it's in the conical flask. So the number of moles of the sodium carbonate in the conical flask will be lower than anticipated or lower than expected. That means that the volume of the hydrochloric acid that you add to it will be lower than expected. Okay, because again, you're just going to need less of it. Then you're going to think, for the exact same reason as the last one, the concentration of hydrochloric acid will be calculated as higher than actual because you need less of it to neutralize the substance. Okay, same concept as the last example. Here's a question from one of the WACE exams. Acid-base titration curve that is produced by an addition of 0.166 mole per liter sodium hydroxide solution to a 20 ml of approximately 0.1 mole per liter diprotic acid. Now, just from that statement, you should be able to work out what's in the burette and what's in the conical flask. Let's have a think. What is in the conical flask? It's the acid. Happy with that? because it's 20 mils. What's in the burette? The base, the sodium hydroxide. Now the sodium hydroxide is our known, and the acid is our unknown. Oops. Okay, so that's a couple of important pieces of information from that. Okay, here's then predict the effect, increase, decrease, or no change on the calculated concentration of the acid for the following two systematic errors that can occur in the titration and justify your choice. So, only rinsing the pipette with distilled water before use. Now you remember you should rinse the pipette with your solution. What's going in the pipette? The acid, which is our unknown. Okay, so you only rinse the pipette with distilled water before use. Your acid is the unknown. So if you've got, that means your acid is your unknown. It has less moles than expected. Okay, if you've got less moles than you've expected, you're going to have a titer that is smaller than expected. If your titer is smaller than expected, that means that you think that there's less moles of NaOH, and by that logic as well, there's less moles of acid. Okay, so if there's less moles of acid, then you're going to expect a decrease in the calculated concentration of that acid. Okay, justification why? Okay, less moles of acid, lower titer, therefore lower concentration of base, lower concentration of acid. Okay, now I know that's only worth 1 mark in this question, but you've got to go through all the processes just to get all your marks. Okay, using an indicator with an endpoint of 4.5. So endpoint of 4.5. Where's 4.5 on this pH scale? This is the titration curve. 4.5 is about here. Okay, now this is a diprotic acid. You're supposed to stop the thing here. So what you've done is you've stopped it here, which is not ideal. You've added less sodium hydroxide than you're supposed to. If you've added less sodium hydroxide than you're supposed to, then again the titer is smaller than expected, which then leads to that, which means that leads to a decrease. Why? Smaller titer, lower titer due to end point being reached before equivalence point. Okay, so, and then state one reason why these errors are classified as systematic errors rather than random errors. Always skew error in one direction. Okay, so here's a couple of questions. You can just look through them, and then when you have a go at them, send me your answer and I'll give them a check. Here's question number 1. Question number 2. You can pause the video to make sure that you can read it and stuff. And question number 3. All right. 1, 2, and 3, they progressively get with less structure, so they might take a little bit longer. See how you go. All right, that was a long video. Adios.